All right, so looking at the next section, it's in your notes, so go ahead and take a peek at that. We have a few blanks here. And today what we're going to talk about is, why do we put salt on the roads in the wintertime when there's snow and ice? Why do you put salt in your boiling water as you make mac and cheese? Not because it's delicious, but it actually serves a point as well. So today we're going to talk about boiling point elevation. In other words, how we can get the temperature of water to boil at a higher temperature, or freezing point depression, how we can get water to freeze at a lower temperature. And I don't want to give it away yet, but there is a way to actually change the temperature in which water freezes or boils at. And now we all know that water boils at what temperature? 100 degrees Celsius. Very good. And water freezes at 0 degrees Celsius. Good. So that's the easiest scale. So it freezes at 0, boils at 100. So if we do a boiling point elevation, it'll boil above 100. Freezing point depression, it'll freeze below 0. So I always want to make sure I point that out. Don't move. They're both temperature difference. All right, so when we talked about solute last time, again, solute is a thing that is being dissolved. And for what we do a lot with boiling point elevation and freezing point depression is we can put a salt in there. We'll talk about the significance of an actual salt tomorrow. Today we'll talk about sugars and fun things like that. And there's a little bit of a difference between salt and sugar. Not that it tastes different, but the way that it behaves. Many of you know what an electrolyte is. Some of you are like instantly thinking, oh yeah, that's the stuff that's in Gatorade, Powerade, all that fun stuff. But really what it is, it's a substance or a thing, an ion, that's allowed to conduct electricity. So the reason why you have electrolytes in your soft drink, or not in your soft drinks, but in Gatorade and Powerade, is because you lose that while you're exercising. And you don't want to lose too many electrolytes while you're exercising, because that's what controls your, sodium potassium pump for your nerves. Something like that. This isn't biology, but you want to keep your electrolytes in check. Colligative properties. So we'll start talking about, there are many different types of colligative properties, and the properties that we're going to talk about is boiling point elevation, freezing point depression. But it deals with the number of solute particles that we have in solution, not the size. So size doesn't matter in chemistry. It's how many particles are present. So today we'll be talking about, actually I'm going to reduce that down just a little. Okay. So tomorrow we'll talk about breaking down salts. In other words, like sodium chloride. We've already talked about dissociating it, and it dissociates into one sodium ion and one chlorine ion, or into 2 ions. If I look at, say, calcium chloride, and this is the green salt that you see on the roads in the wintertime. And we'll talk about why we use calcium chloride versus sodium chloride tomorrow, so I'll leave that as a little cliffhanger for you. But when that dissociates, it dissociates into calcium ions and chlorine ions, or a total of 3 ions. More bang for your buck. However, if you have this big sugar molecule, sucrose, it doesn't dissociate, it just simply dissolves. So what happens is, even though there's, 24 different atoms in there, it stays together as one molecule. So if I were to place this on the roads, it would just make one big sticky mess, number one, but it wouldn't do an effective job. And we'll talk about how that takes place in a few minutes here. So it's the number of particles, not the size. And again, this is a pretty big molecule versus, say, one of these two. All right, we've all talked about molarity, but now we're going to talk about molality. Okay, it's not me mispronouncing it. Molality is similar to molarity in that you have your solute over your solvent. But the big difference here is it's not, or what is molarity? Somebody tell me, remind me of what molarity is. It's moles per what? Molarity. Molarity is moles per liter. Very good. That's what molarity is. What we're talking about with molality is it's moles, and it's a little m, not a big M, but it's moles over kilograms. And that's the difference. And we'll always be talking about water, so that's one nice thing. And I think we only talked about water in AP. Well, we actually took this out. But it'll be kilograms of water. Now, the reason why they talk about molality versus molarity is when you're working with molarity, the temperature doesn't change. Anybody know what this thing is? It's a thermometer. Anybody know the actual name? It's a Galilean thermometer. And Galileo is actually given credit for this type of thermometer. And what we have here is just water. And inside of here there are little bulbs with different liquids in there. And there's a certain amount of a liquid in each of those. So each of these little bulbs has a different density. And that mass inside the bulb doesn't change, regardless of whether that liquid starts to evaporate or not. That mass within that volume doesn't change. However, as the water heats up, what happens to the density of the water?
It's warmer.
The density. What's that? Gets thinner. In other words, those molecules spread out farther and farther away. So you still have the same number of particles, but as water heats up, it actually expands a little bit, and therefore the density of the water goes down. As the water gets colder, what happens to the particles or the molecules? They actually get closer and it becomes more dense. So as this water gets more dense, more of these bulbs will start to float. So you always read the one that is the lowest floating. And this one here says, and it's not very accurate because it goes like 4-degree increments, but this one's 75 at the lowest one. And that's about pretty close what this room is. It's pretty toasty today and it's pretty humid outside and it's very uncomfortable. The highest one is 79, so that's kind of nice because we read the lowest floating bulb. These other ones have sunk to the bottom because it's too warm for them to be floating. So what we want to focus on when we talk about molality is that since the density of this liquid changes, because we are changing the temperature of this liquid, that we're not concerned about the volume, which remains the same when we're working with molarity because the temperature remains the same. So we still have the same number of water molecules that are present. In other words, that mass doesn't change, but the volume will. So that's the main difference between why we talk about molality with freezing point and boiling point changes, and we talk about molarity when we're just strictly working with concentration. Here the temperature doesn't change, here the temperature is changing by a lot. So we can't say, oh, we have a certain volume, we want a certain mass. It's not a big deal. So we just take whatever amount of water we have and convert it into kilograms, and we still have our number of moles. We dissolve that in. Everything's happy. Easy. Still easy, yeah. All right. So let's look at a practice problem. So the first practice problem says how many moles of sucrose, which is C11H22O10, and you would not ever have to memorize that, are there in a 2.33 ml solution made with 1,450 milliliters of water. So again, our equation is, we have molality, which is the number of moles over kilograms. Okay. Now, just like when we worked with molarity, if you know the volume and you know the molarity, always start with the volume. Well, in this case here, we are given a volume. What can we do, or do we have a conversion that we can get milliliters of water to, say, grams of water? Anybody remember that conversion? I gave it to you on a quiz or a test not too long ago. Yeah.
So like 1 milliliter equals 1 cubic centimeter.
1 milliliter equals what?
Like 1 cubic centimeter.
Okay, so that's still volume to volume. Did I give you how much that weighs? That's true. Anybody remember how much 1 milliliter of water weighs? What is it? You're all going to hit yourself in the head once I tell you. 1, good. It's 1 gram. Okay, so that is the standard for water. 1 centimeter cubed or 1 milliliter of water equals 1 gram. And again, this is pure water. So if we know we have 1,450 milliliters of water, how many grams of water do we have? 1,450 milliliters of water. Do we need to go through that?
Yeah.
Probably wouldn't be a bad idea. So we'll start off with what we know, the 1,450 milliliters of water. Convert that into grams. So 1 gram of water is 1 milliliter. If I stopped right there, what do I have unit-wise? Grams. I need to get it to kilograms. So how do I convert that? Grams to kilograms. Which one's bigger? Kilogram. How many grams in a kilogram? 1,000. Good. Now, here's what's cool. We know the molality, and the molality in this case is 2.33 moles per kilogram, right? Where would it be a good place for that in this equation? Next step. Because again, you're moving your kilograms diagonally, and moles go right there. So we'll take our 2.33, pop it right in there. And this tells, and the question's asking for what again? How many moles? Yay. Do we have the unit moles here?
Yeah.
Isn't this easy? I like it. So we'll say 3.8, and that's moles. Think you could do that on a quiz next Monday or Tuesday? It's not hard at all. Yeah. The hardest part is knowing that molality is moles per kilogram. That's the hardest part.
That's pretty tough.
And knowing that 1 gram equals 1 milliliter, which also equals 1 centimeter cubed. And that is for water only. Okay? That's for water only. Don't try that with anything else. Okay? All right. Well, let's look at another one. Ooh, here we go. Next practice problem asks, how many grams of magnesium carbonate are there in a 0.25 ml solution made with 850 grams of water? Well, the question wants to know how many grams of magnesium carbonate. Well, let's first of all write out the formula for magnesium carbonate, which might be very beneficial here. What is magnesium carbonate? Well, what's magnesium?
Mg.
Good. What's the charge on magnesium?
Plus 2.
+2. Good. Okay, so we have a +2. What is carbonate? CO3. What's the charge on that? I hear -1, -2. Which is -2. Good. So it's balanced as written. So that's magnesium carbonate. Okay. The question wants to know how many grams of magnesium carbonate. So let me ask you this: do we know the mass and the molality?
Yeah.
So it's kind of like knowing, if you know the mass and the molality, it's kind of like knowing the volume, except we're starting really here without showing that. And we can change the grams into kilograms and then find out how many moles. So we can actually work backward here. So if you know the grams, and keep this in mind, if I'm giving you a gram amount within the problem, it's always going to be for water. Okay? Make sure that you're doing it, unless I'm asking you to calculate molality of the substance. And then I'll be very, very specific on that. So we can start off with our 850 grams. And again, this is of water. So it's just like if you have your volume of water and you know your molarity, it's going to cancel out anyway. So we need to convert this into what? Kilograms. Good. So 1 kilogram is equal to 1,000 grams. And then we'll plug in our 0.25, and this 0.25 can be represented as 0.25 moles for every kilogram. That's what that little m represents. So let's put that in there, 0.25 moles. And I'm going to go ahead and put magnesium carbonate on there. And that's per kilogram. But the question wants to know what? Not moles, but
Grams.
So how do I get the grams from here? Yeah, do your mole. So 1 mole of, sorry. Yeah, no, that's right. So 1 mole of magnesium carbonate, and then go to the periodic table. Let's find out what these things was. All right, so the mass of magnesium is 24.3, and carbon's 12.01, and of course there's, let's change that color there. So the whole thing is, what is that, 84.12. And then when you type that all in, you get like, what, 17.9 grams? Or did anybody type that in yet?
Yeah, I got 17.9.
You got, yeah. And that's 17.9 grams of magnesium carbonate. Okay. Sorry, that's actually 84.31. Whoa. Well, that's interesting.
That was cool.
31 grams, sorry. Oh, now the sun decides to come. All right, so the 4s are part of your homework. Yay. All right, calculations dealing with colligative properties. You will be given 2 equations, and you'll also be given 2 constants. See if I can blow this up a little bit. Oh, isn't that good looking? Let's see here. Let's let me actually write out this formula for you. Okay. So we're going to be working with 2 equations, and we have delta T, and it's sub B. I wonder what that means, sub B. And we have a constant KB times little m. Okay. So you have one of the equations that looks like that. The other one looks like this, where it's delta T sub F, and it's K sub F, whoops, times M. Okay. Now, the delta T stands for the change in temperature. What do you think the B stands for?
Okay.
Boiling. Very good. And F?
Freezing.
Freezing. You guys are on it. So this is the equation that we use for the boiling point elevation. This is the equation we use for the freezing point depression. In other words, when the temperature gets lower. There's also 2 constants that are given. And let me move you over. Now, we'll just raise that. The constant is your K sub B or your K sub F. And they look something like this, where it's very similar units except the value is different. So the KB is 0.51, and it's degrees Celsius, kilograms over moles. Okay. Now, it's the inverse of the molality when you look at kilogram moles. So that has been flipped, but the the change in temperature is on top. So it's really a very simple plug and chug type thing. You have to find out the molality, use the correct constant, and the K sub F is like 1.86, I believe, degrees Celsius, kilogram per mole. So you just have to use the correct value. So just make sure you look at your sheet. And I think I have these values on the back of your periodic table. I do. They're right down here on the bottom. And your K values are where? Oh, over here on the right. So you have those values on the back of your periodic table, which means you'll have them on the test and quiz as well. So we just have to be able to use those values. Okay. And as a reminder, if the boiling point is 100 degrees Celsius and the freezing point is 0 degrees Celsius, if we are doing a freezing point depression, we are lowering the temperature which it freezes at. If it's a boiling point elevation, we are elevating the temperature. So we're moving away from 0 and 100. Some of you might say, oh yeah, I kind of like that X to be right here. So we're going to raise the temperature which it freezes at. That's a whole different conversation. And here, we're going to make sure that if we're doing something at a freezing point, it's getting lower. If we're doing something at a boiling point, it's getting higher. There are ways that we can reverse these arrows, but we're not going to do it in here. We're going to keep it simple for you guys. Okay. And were there any blanks? Were there any blanks on that? Oh, difference? Did you guys get that one? All right. Let's look at the examples. Which is somewhere. There we go. All right, so the practice problem, and again, you'll have access to those. The question asks, at what temperature will a sucrose solution boil if it contains 175 grams of sucrose and 750 milliliters of water. Now, what is not given to you is the molality. So we have to find out what the molality is first. So we have to actually find out what little m is equal to. And in this case, it says we have 175 grams of sucrose in 750 milliliters of water. Is it possible for you to determine how many kilograms of water we have without showing any math? Some of you may need to show the math. Is it possible? No? Okay. Well, let's do that. So 750 milliliters. What's the conversion from milliliters to mass? 1 milliliter equals 1 gram. And then how many grams in a kilogram? 1,000. Good. So now that you have seen this, I bet you're going to go, yeah, I can do that. So what's that value? 0.75. Very good. Okay. Everybody see how easy that is? So move the decimal place over 3 places to your left. So if you have 750, it's now 0.75. If you have 7,500, then it's 7.5. So, but if you still need to show that, so you don't do something dumb, please continue to do that. What we do need to change is the grams of sucrose into what? Moles. Because again, don't forget, molality is moles per kilogram. So we need to change the 175 grams of sucrose, and the formula is right there. So we'll go 175 grams of C11H22O10. That is a fun one. So 1 mole is, actually I'll write that down. So it's 11 times 12.01 plus 22 times 1.008 plus 10 times 16. That is, so the molar mass is 314 point, what is it? 286, yeah. So if I take 175, okay. So we have our number of moles. So your molality, and you have one of 2 ways of showing this. You can, what are we doing, boiling? Yeah, we're doing boiling. So we can do K sub B, sorry, delta T. Delta T sub B is equal to K sub B times the molality, which in this case, our K sub B is 0.51 degrees Celsius kilogram per mole. Another fun unit there. And then we can multiply that by either plugging in those values. I'm just going to leave it as this, 556 moles, or whatever's in my calculator, divided by 0.75 kilograms. So what happens to my units? Let's take a look at the units real quick. What happens to the unit moles? Cancel. That's why we show our units. What happens to the kilograms? They cancel. That's why we show our units. What unit remains? Degrees Celsius, which is a temperature value. Okay? That's why you show your units. So you make sure that you're doing this correctly. 0.378, and that's degrees Celsius. Now, so here's what we have to do. We're not done yet. Since this is our change in temperature of our boiling point, is the temperature at which the substance is going to boil, is it 0.378?
No.
No. It's going to be elevated at that point. So we have to add it to whatever the boiling point is, which is 100. Boiling point elevation, you add to 100. If you're doing a freezing point depression, what are you going to do? Subtract from 0. Very good, not 100. So you're not done when you finish working out the math. So in this case, adding all that sugar is going to raise the temperature at which water boils to 100.378. When doing this, change your value for water to kilograms. Change your mass, or whatever I've given you, of your solute. Make sure you can distinguish that water is the solvent, where the sucrose is the solute. So it's always solute over solvent. Okay, so we've talked about that already. Just a reminder. Number 2, at what temperature will a methanol solution in methanol CH3OH freeze if it contains 55 grams of methanol in 1200 milliliters of water? So the only difference here is the equation that we're using. We're not using the delta T sub B, but we're using the delta T sub F because it says freeze. So you have to pick up on that. The equation's very similar, except now we have K sub F, which is a constant, times the molality. Okay, the K sub F is already given to you at 1.86. Again, that's degrees Celsius. Oops, sorry, kilograms on top. Kilogram mole. But we have to find out what the molality is. So how do we find out the molality? Very good. Change the grams of CH3OH into moles. So we have 1 carbon. We have how many hydrogens?
2.
4. Very good. Total. And we have 1 oxygen. Everybody see that? How I got those 4 hydrogens there? Then this molar mass is 32.042. So we'll take 55 divided by that. And that equals 1.7. We'll say 2. And that's moles. Okay, so now we have in our equation up here, we have 1.72 moles. Now, of course, you wouldn't retype that. You have that in your calculator, so you can quickly retrieve that. How many kilograms of water do I have? Very good. So take the decimal. You know 1 milliliter equals 1 gram. There's 1,000 grams, so boom, right there, 1.2. Check your units real quick. Kilograms cancel, moles cancel. 2.66?
Yeah.
Okay. So 2.66. Now what do you do with that? Subtract it from 0. So we have our freezing point is 0, so we're going to subtract that. And so water now freezes at negative 2.66 degrees Celsius. Brr. Isn't that fun?